Use of keratoprosthesis in complex corneal blindness has significantly grown over the course of the last decade, both in India and overseas. Despite multiple advances in the K-Pro design, better understanding of the tissue reaction still remains a big challenge. Such good outcomes after K-Pro is quite common, but the two most important challenges for all K-Pro surgeons are infection and corneal melt. Literature search showed that all the studies were centered around changing the design of K-Pro to prevent melt or infection, but none on improving the strength of the donor tissue to resist the melt or infection. Only a few articles quoted about the cross-linking of the donor corneal tissue. But what interested us was glutaraldehyde, as it was the gold standard for cross-linking in vitro. Tissue engineering of human corneal equivalent have been carried out with significant results, with collagen being treated with glutaraldehyde. Studies done comparing GA with other methods of cross-linking like genipin or collagen cross-linking showed that their cross-linking effect was nowhere near that of glutaraldehyde. Glutaraldehyde is a linear 5-carbon dialdehyde present in various concentrations ranging from 2% to 70%. After extensive research, we found out that 0.5% glutaraldehyde had the maximum cross-linking effect. Glutaraldehyde is allowed to react with the free amino groups in the collagen. When this happens, Schiff's base is formed. Schiff's base produces hydrolytically stable compounds which causes the cross-linking effect. When you increase the concentration and the exposure time, glutaraldehyde forms pendant GA links, and these are weak links and have no cross-linking effect. The purpose of our study was to investigate the possibility of induction of cross-links in donor corneal tissue in order to increase the stiffness as a basis for an ingenious technique of keratoprosthesis. 3 strips of donor corneal tissue was taken from the same donor. The first strip was treated with 0.5% glutaraldehyde for 5 minutes. The second strip underwent the regular cross-linking, that is 3 mW per centimeter squared, for 30 minutes. The third strip was kept in BSS as a control. The treated tissue underwent the following 3 tests: the stiffness test, durability test, and the tensile strength. In this test, the tissue is simply held with a forceps to see its strength. Here we can see that the tissue treated with GA showing a better stiffness, followed by the tissue treated with cross-linking and the BSS. In durability test, we used 20% KOH to digest the tissue. The disintegrating time was noted simultaneously for all the 3 treated tissues. The tissue treated with BSS dissolved at around 2 hours and 3 minutes, followed by the cross-link treated tissue which dissolved at around 3 hours and 55 minutes. The tissue treated with glutaraldehyde resisted disintegration till 12 hours and 44 minutes, thus proving that the glutaraldehyde treated tissue was the most durable one. As all these tests were only qualitative, we did the tensile strength for the tissue to quantify the strength. We collaborated with the PSG tech who had a 10 kN machine to measure the tensile strength. The length and breadth of each treated tissue was accurately measured and placed in the throngs. The tensile strength was measured till the tissue gave away during the test. After placing the BSS treated tissue in between the prongs, the tissue is stretched to test their tensile strength. The tensile strength is measured graphically and noted. Until the tissue resists, we can see the graph very steadily rising, followed by a downhill trend when the tissue breaks. Similarly, the glutaraldehyde treated tissue is tested. The difference here is that you can see that the tissue resists breakage, and you can see the tissue slipping from the prongs rather than the tissue tearing and snapping away like the BSS treated tissue. This graphical representation shows that the glutaraldehyde treated tissue resisted elongation the maximum time when the separation force was applied, proving quantitatively that the GA treated tissue had the maximum tensile strength. The donor corneal tissue is first soaked in BSS for 30 minutes. The tissue is pre-treated with 0.5% glutaraldehyde for 4 to 5 minutes in an IOL tub. After treatment, the tissue is thoroughly washed in normal saline for 10 to 15 minutes. The routine K-Pro procedure is performed. Care is taken when the 8 mm and the 2.5 mm donor punch is used, as the chance of slippage or decentration is very common as the tissue resistance is very high. Do not apply too much force over the back plate or the titanium ring as it can get damaged due to a stiffer donor cornea. In the patient, the graft size and trimming the host cornea remains the same. Suturing is a little tough and care should be taken as the needle can bend due to the increased resistance of the donor corneal tissue. Usually 8 sutures are sufficient as the tissue gives a watertight fitting. We performed around 10 cases and had a follow-up of 1 year. We included all types of cases including multiple graft failures, vascularized leukomatous opacities, Stevens-Johnson syndrome, and chemical injury with limbal stem cell deficiency. During this period, we report no early adverse effects of glutaraldehyde. Better understanding of the mechanism of the action of glutaraldehyde has helped us to use it judiciously. Early results are very encouraging. Glutaraldehyde is definitely a promising cross-linking agent which strengthens the donor tissue and increases the durability of K-Pro. I finally want to thank Dr. Dolman, Dr. J.K. Reddy and the Aura Lab for their constant work to help the blind people to regain light and life.